Hi everyone. Delighted to be joining you around midday from Palo Alto, California. Thanks to Nick and Otto for inviting me to do this keynote in this very crazy, strange year for all of us. So this talk is unlike my other keynotes where I often synthesize ideas from various projects. I'm going to talk about a specific effort to design a curriculum focused on topics that we consider as advanced for high school students. And along the way, I'll share how it connects to gender equity, integration with data science and other subjects, and teacher PD. A little bit about myself. Looks like this is how Google would present me if you Googled my name. So I guess us folks in research and academia are identified by our citations and H-index and publications and whatnot. They did cut a few corners with my affiliations and my identity, I guess. I'm a computer scientist and learning scientist by training. And my work in CS educational research focuses primarily on the K-12, which is the primary and secondary years. And though I started off in after school and informal settings, most of my research in the last decade has been in formal classroom settings. And you'll already heard my official affiliations. If you want to learn more about my work or whatever, my very infrequent blog posts, you can go to shuchigrover.com, and that's my Twitter handle. So first things first, I want to acknowledge the National Science Foundation for funding the work that I'll be presenting and these wonderful collaborators on this work that I'm presenting. And Brian and Akosh there deserve special mention, as you will see in a bit. But really, our team includes teacher partners as well. So thanks to them as well. They remain anonymous as I also present research from our teacher PD as part of this keynote. So this address is going to be a bit of a juggling act. I'm going to talk about CS in high school in general, which sort of describes the rationale for why we took the approach we did and motivated our effort called CS Frontiers, which is basically about teaching advanced topics in CS, distributed computing, AI, machine learning, Internet of Things, cybersecurity, and such. And I'll focus on our work on the distributed computing module. And then I'll go to the how of our approach, which focuses on the tool and pedagogy, the tool being Nets blocks. And finally, in a small shifting of gears, I will share our experiences from this past summer when we worked with teachers on a PD program that also involved co-designing lesson plans in preparation to teach distributed computing. So in the spirit of this keynote, I hope that you will see this as a template or a prototype, even if you, don't necessarily care too much about these particular courses. There are bigger ideas on CS instructional design and tool design and PD design that you can take away, though these are in this keynote concretized in the context of CS Frontiers and through first principles, which is sort of a framework that can guide the design of successful CS teacher preparation. And by PD, I mean professional development. I think everybody knows that. PD efforts for constrained times, such as now during a global pandemic, but at other times as well. So the discussion is centered on course design, as you may have guessed by now, and starting with the rationale, we'll talk about how it influences our topics and concepts to tools and pedagogy, which kind of influence each other, and then to the curricular sequence, and then that captures the content and pedagogy, and then finally teacher PD. So the context for this work is high school computer science. And now I don't know how it is in other countries, but I'm going to be situating everything here in the US. And high school CS, as in other levels of primary and secondary school education, is currently in the US, guided by the goal of ensuring that all students basically have the opportunity to learn the foundations of computer science, to do this in ways that are engaging for all learners and build interest, and are equitable, which basically means that we actually need to pay additional attention to groups that have historically been marginalized from computing, which means girls, underrepresented minorities, people of color, Blacks, Hispanics, Native Americans, and such. And in the US, there's also this idea of the advanced placement courses for high school, which is for students that want to drill deeper and take courses that roughly map to the intro level courses in college. So let's see how we are doing on this right now. For courses and curriculum, we do have basic foundational courses like Exploring Computer Science and Code.org, CS Discoveries, that we hope all students will complete at a bare minimum before they graduate from high school. And often these courses are geared towards students that don't have much prior experience with computing. But then for students that do have more experience and that are more interested in CS, we have advanced placement courses, and we have two of them. One is the newly developed CS Principles course, which has a focus, in addition to programming, on concepts like how the internet works, societal impacts of computing, and so it sort of maps to a CS0 is what the broad understanding is. It's a broad curriculum, but it's designed to engage all students. And then we have APCSA, which is a course that has been around for decades now. It's an intro college level computer science course. Over the years, it has been taught in various languages. Currently, it's basically a Java course. And it has a reputation for being pretty dry and unengaging. And it's really popular only among students who are great at CS, plan to major in CS in college, have a fair amount of prior coding and experience. And I think you can already imagine what that demographic is that cares to do CSA. And how are we doing on these other measures on equity and motivation? Well, on equity, we still have a very long way to go. Here I'm focusing data on mainly, by gender, but the story is just as troubling when we look at other demographic data such as race and ethnicity. And you see the numbers. Those are the numbers from the entire country that took these exams in this year, this summer. And APCSA and CSP, those are the numbers. And just for comparison, I've put the numbers for the two calculus courses, AB and BC, which is BC is an advanced calculus course. And you can see that even that advanced calculus course attracts many more girls than even APCS principles, which is supposed to be our very engaging course. And of course, APCSA bombs abysmally when it comes to attracting females. And so it has the CS courses have the lowest numbers of all STEM subjects. And this is a statistic I just came across recently. Less than 30% of California's high school CS students are female. So there is a lot of gender inequity, and put simply, advanced CS courses are basically still dominated by white and Asian males. So on motivation and interest, like I said, Principles does well, but students completing Principles have no good options to drill deeper into CS in a course that is engaging and inviting and motivating, because CSA isn't. And in general, in K-12, we don't seem to be doing well on gender equity or in other kinds of equity. These are results from a recent Google Gallup poll that came out just this month. And as you can tell, we're just not doing a great job to motivate students to learn CS or help them see CS as an important subject, in spite of all our good intentions and efforts over the last few years. So we need to be doing better to help students see CS as relevant to all, to various topics and subjects, to be seen as inviting and accessible to different groups of students with varied interests, and to be seen as exciting through topics that are motivating. And so on the issue of gender equity, when courses are optional, as they are in high school, we really do need to work harder to recruit and engage girls through conscious efforts, through appropriate pedagogies, and by providing environments that are supportive and nurturing and inviting. And we know there's a ton of research in the learning sciences on how we can engage girls in STEM. It's not a problem that's sort of unique to CS, but CS seems to be, suffering more currently, and how attention to socio-emotional factors and sociocultural factors really does pay off. And these are some of the suggested strategies: project-based learning with opportunities for collaboration, the idea of interacting with role models and students seeing, representations of themselves, people like them in the field, to envision their own future selves, as Marcus and Neurius would have put it, and then working on projects that are meaningful and socially consequential, STEM for good. And a recent research by Catherine Childs shared in the Raspberry Foundation seminars shared that girls tend to prefer more structured initial activities. They don't like open-ended exploration so much. They want a supportive ecosystem, basically. They need it with parents, teachers, people around them, sort of encouraging and nurturing their interest. And it's all about basically empowering girls into working in STEM. On the issue of engagement, think for a moment what students in high school like to do. I mean, what are the ways in which computing intersects with their lives? What might they find motivating? Multiplayer games, online multiplayer games, they play them all the time. There's social media, they share things over the internet. There's images, music, chat, text. They rely on recommendation engines for their movies and music and YouTube videos and online shopping that use their own user data to tailor their online experiences. They rely heavily on AI and assistance. If my own children are anything to go by, they're always, asking Siri and Alexa and what have you. And they do have these interesting ways to sort of create strong passwords. They understand that there is such a thing as cybersecurity and issues of privacy and security that are relevant. So basically, it's in all these ways that computing dominates our lives and students' lives. And yet these are out of reach of high school students. And in fact, even in college, it's only available to CS majors. And after the first couple of years, at least here in the US, as electives. And we're really depriving students of authentic engagement in topics that we believe are too advanced, that could be pretty exciting and motivating. And that's something we should remedy. And so that's what motivated us to embark on this effort to design a course that we call CS Frontiers that would provide, exciting, engaging pathway for high school students as an alternative to APCSA. And CS Frontiers is a modular project-based curriculum that would bring high school learners experiences in distributed computing, AI and machine learning, cybersecurity and Internet of Things. This particular module also focuses specifically on healthcare. And finally, a module that gives students the opportunity to learn about software engineering and work on capstone projects that sort of employ ideas from these modules. And so these are the essential ideas and philosophies that underpin this, I had it coming up nicely, yes. Engage girls, engage in data science, project-based learning, collaborative activities, and transdisciplinary learning. And on this issue of transdisciplinary learning in the classroom and helping students see relevance of studying CS, I want us to engage in a bit of a thought experiment. I'm not sure about the answer to this, but we often talk about integrating curriculum coding into other subjects. We talk about taking coding and CS into science and math classrooms and social studies. But what does it mean to bring these other subjects into a CS classroom, into a high school CS classroom, to have students wrestle with questions from another domain that may be of interest to the student and motivate the learning of CS concepts through that? And I think this gets to the idea of framing, which is important. Framing a learning experience, we know from the learning sciences, impacts learning, it impacts engagement, it even impacts transfer. And so when students see CS concepts, learn CS concepts in context, in the CS classroom to address issues of another domain, they see CS in an applied context. And I think that is valuable as we prepare learners who may have interest in other fields, not just computer science. And that sort of gets at our goal of broadening participation as well. Okay, so coming to the tool, what kind of a learner-friendly tool? Let me take a sip of water here. Will help us accomplish the task of teaching these advanced concepts to teens. And I want to remind us of this 1982 quote by Dijkstra that I think is still very key to CS education. And it was mentioned and explained more recently in this Communications of the ACM article. There were other truths in that article that Dijkstra had written that were pretty controversial and have become very controversial, but this one no one debates. That tools make a difference on how we think, our habits and our thinking abilities. And so luckily for us, we have a tool at our disposal that makes all these complex ideas very accessible to high school students. Drum roll, please. It's called NetsBlocks, and it's the brainchild of Brian Broll, who, with his PhD advisor, Akush Ledeczi, at Vanderbilt University, created this tool, which basically brings down the walls around a popular introductory programming environment and enables the environment to basically embody these goals of collaborative, a collaborative educational environment that provides for accessible distributed computing. And so NetsBlocks extends the SNAP environment that many of you probably know about. It's a popular block-based programming environment. It's used as a novice learning environment at various levels of K-12. It has a Scratch-like interface. It's been built on Scratch, and it's the environment that's used for the beauty and joy of computing high school curriculum, APCS principles curriculum, and which means that a lot of students and high school teachers are already fairly familiar with SNAP. And so NetsBlocks basically opens up SNAP to the internet. And through doing that, it really unleashes a world of possibilities. And to me, bringing down the walls makes it like this very accessible, but very powerful protean tool with which we can do all these kinds of things: communication through message passing, chat rooms, data science, cybersecurity, distributed computing with web and data, web APIs, data services, real-time collaboration where students are actually co-editing the same program, not sitting side by side, exchanging roles, and things like robotics and AI, etc. And so because this is, what our curriculum depends so heavily on, I'll explain this innovation as a backdrop to our instructional design. So I'll spend a few minutes talking about NetsBlocks. So NetsBlocks basically achieves this through two simple but very fundamental abstractions. The first is remote procedure calls. So it's basically call functions to the server. So it's a call like temperature, temp, to a service called weather. And similar RPCs are grouped into a service. And these RPCs take input parameters, and they work just like any other custom block. And it really is just that simple. It's a call block, and the way it works is that the call block accesses the NetsBlock server, which then accesses the internet, sends the request to the appropriate API, and then the result that it gets back gets routed back to the NetsBlocks client running on the user's computer. And but through this simple abstraction, it basically opens up a world of projects on climate and science and astronomy and geolocation and maps and even movie database and Pixabay internet, anything that has a web API basically, and not just web API, there's a way to bring in data sets as well, robotics and traffic and Twitter and stock exchange and whatnot, all kinds of stuff. And so, and you can also nest call. So in this first very simple example, we have a call to the climate service, the Mauna Loa carbon dioxide data from the Mauna Loa Observatory, which, it's publicly available data from the NOAA service in the US, the National Observatory, National Oceanic and Atmospheric Administration data set. And it routes that data to a chart service, which is basically uses the GNU plot to draw this. And imagine in just that one call, and you switch costume to basically change your backdrop of the Snap stage, and in that one call, basically two blocks, you have created a visualization of carbon dioxide that basically, kids are very passionate about climate change projects. And this is just one example of something that, it's such a low floor, and it suddenly brings, a lot of excitement to what students can do. Here's an example from a distributed computing camp that we did this summer with high school students. And it accesses, the Google Maps and geolocation and the weather service. And students also included things like Google Translate of their own accord to sort of translate the message that they provide on the screen and whatnot. So there's weather related stuff. And as you can see, getting and displaying maps is basically as simple as a call to Google Maps with lat-long data and the size, and then you just switch costume and you change the backdrop. And in similar fashion, you could be navigating and observing astronomy data, the sky map. And here's an interesting example of the movie database. Students are fairly interested in movies, and they enjoy making trivia games or quizzes as part of their, CS apps. And these movie trivia games can be pretty exciting and can actually probe many, many different facets of movies, because the movie database really does bring back a whole ton of data. And imagine also how something like the movie database can become a source for discussing topics of social and racial justice. You don't just have to show a movie like Hidden Figures. You can actually have students creating a project about it. And they could also interrogate things like racial representation in Hollywood and the movie industry, or gender equity. These have all been topics of discourse, current discourse. And so the possibilities truly are endless. And this one example, I wanted to go over to the internet, to NetsBlocks, switch over and actually, demo one of these. But I'm scared about this whole setup with the screens and all of that getting messed up. So I think these screenshots will have to do. But this is really topical. This is COVID data from the Johns Hopkins database. And it shows how students can engage also in data practices, because now the COVID data, that is brought in undergoes some sort of pre-processing. You see that process data, block that you can provide as an abstraction to students, or you can have students do it on their own, which becomes an exercise in data science in and of itself. And they basically create this visualization. This is back from August, from a talk that I did in August. I took the screenshot back then. But this is from cases in India, and of course I think now we are all on a third peak around the country. This was the second one hump that we were coming down at that time. And basically students engage in visualization, and they work with abstractions like lists and multi-dimensional lists, which is really very cool to be able to do at the high school level, at the advanced high school level, because they don't really have opportunities to do it in a very authentic setting like this otherwise. And so I think by now you are getting a sense for the number of topics and domains in addition to data science that can be brought into the CS classroom in this way. And speaking of integration with data science, I want to share something from this framework that I talked about and wrote about this summer for integrating computing into other subjects. So there's the disciplinary concepts and practices, the CT, and the pedagogy. And I highlighted that often data is a crucial vehicle for integration, where students work with data that is from or relevant to a domain, for example, COVID data or demographic data or weather data, and you can answer questions from the domain and critically examine phenomena in the process, social or scientific. You can engage in evidence and database reasoning, and recognize patterns, make predictions, and work with the data representations and abstractions, as we just talked about, and do tons of data analysis. And I want to say that data is increasingly being seen as a great vehicle for teaching key data science skills, but are also very relevant today, and being seen as a way of teaching computational thinking, and even emerging topics like AI. Sriram Krishnamurthy and Kathy Fissler have authored a couple of articles this past summer on that. And so we are here using it to teach AI and distributed computing and etc., all around data as the linchpin. And that's great, because data really is everywhere, and NetsBlocks and CS Frontiers truly opens up so many opportunities for transdisciplinary learning once you basically have data as your your corner, the linchpin, so to speak. And it affords students the ability to work on projects of their interest, including something as local as the community they live in. And that's because NetsBlocks actually helps students create their own service if you have access to a data set as a CSV. And this to me is really what makes NetsBlock so cool and powerful, because all you have to do is import the CSV into Snap, which creates a table, a list of lists, and pass that data structure to a service creation service that creates a new service that can be used as an RPC in the call block. And it shows up under the community item under your own username. And then you can be creating your own project based on data of local interest and student interest, or anything really. So moving on to the other abstraction, the other one is message passing. So many of you may have seen how events work in Scratch and Snap. You have a broadcast and then an event trigger, which is a when I receive that particular message. And so messages in NetsBlocks have these two blocks, which is a send message, which is a customizable block. And in that you can create messages of various types with however many parameters, etc. And a sender, a receiver parameter to receiver. And the event trigger for the receiver is when I receive, and you can basically take action on that. And this is that message type editor. For example, you may have a chat message type, which has the fields sender, time, message, etc. And connected to this idea of distributed applications is also this notion of a room. And the room basically defines the local network for the application. And the room contains a number of different roles, which are basically named clients in this distributed application. And each client is basically analogous to a block-based programming project. For example, a chess game may consist of two roles. One is the black and the white, which represent the two players in the game of chess. And then you pass messages between, those, and you can only send messages to those folks these users or to the entire room. If there's more than one person, then all of them get the message. And a new instance of the room is created for every new run of the application. And this again has a very low floor. So look at how a simple chat app can be created. You basically do send a message with the username, with your username and what the message is. And then, the receive basically could just receive the message and print it out on the screen or whatever. This is like the simplest version of the chat app. And it's so simple to put together. But there's also a very high ceiling, as with RPCs. You allow the user to create complex distributed applications across the internet, like dynamic chat rooms where people come and go. And there the issue of addressing, becomes something relevant that students learn in a very organic way. They learn about protocols, latency, etc., peer-to-peer networking, multiplayer distributed games like Battleship, Pong, tic-tac-toe, lots of them, and even robotics. So, in fact, Roboscape is a service that has been added to NetsBlocks to control robots via Wi-Fi, and robots communicate with the program through messages that pass the sensor value or whatever to the program, and then the program communicates action through the sense-act paradigm. So what the robot should do is send as a message from the program, from the NetsBlocks program to the robot. And again, and obviously this opens up this whole world of cybersecurity where you can sort of listen into others' communications and hijack them. And in fact, these camps have been run very successfully with students, cybersecurity camps. And so this is a screenshot of the Battleships game. As you can see, it's basically, you're basically sending messages of when the other player is ready. You send the message to say, it's basically turn taking, and you pass the baton or token back to the other player. And that's how you basically communicate whose turn it is. And you also communicate what the latest state should be in terms of where your whatever knots and crosses or battleships or whatever need to be. And in the game of Pong, which is very popular, you can actually have two students playing across different machines where one is controlling the left paddle and one is controlling the right paddle. And again, you have, a way of coordinating the turn taking and such. Another great feature of NetsBlocks is its ability to allow students to collaborate on the same project, like in Google Docs. And so you can do concurrent editing and you can work together on a program, but it executes on each computer is separately, independently. All students are drivers, and there has been research done. I'll just share the paper in just a moment on how students find this to be more engaging than, say, a pair programming or, where there's a driver navigator thing that has to be, you know, done, and students have to be co-located. But in this particular case, you can have students that are not co-located and they could be collaborating across, which, especially in COVID-19 times, but even otherwise. And of course, it provides opportunities to demonstrate things like latency and conflict resolution. What if both students are working on the same block at the same time? I mean, there aren't many conflicts that occur the way this is designed, but it does provide that opportunity. And in addition to the create your own service, the way NetsBlock's architecture is designed, it's modular, and basically you can add more services and more connections to other tangible computing or other hardware, IoT, et cetera, et cetera, et cetera. So there's a lot of work that has already, papers that have been written. It's about 3 years old. It's been, and folks have written papers on cybersecurity and collaboration, et cetera. And I encourage you all to check these and many papers on NetsBlocks. So coming back to our course, CS Frontiers, which is basically powered by NetsBlocks, we basically, believe that since everything that students interact with online is distributed and networked, we feel that distributed computing it's a very fundamental idea to teach to high school students. And the way we've designed this course, it allows users, learners to access a wealth of data on the internet, which basically means that we provide many entry points for many interesting projects of personal relevance and interest even. And they can create meaningful apps or multiplayer games, distributed animations. They can collaborate, through pair programming or group projects. And the goal is basically to increase motivation, combine CS with other disciplines, open up a world of interest and data-driven inquiry, enhance collaboration, empower learners, especially girls. And this is the 9-week modular sequence that we have roughly designed as of now. And the pedagogy that underpins the lesson plans and the sequence is basically project-based learning, guided projects, and projects of student interest, culturally relevant pedagogy, because the moment you bring the learner-centered work, learner-centered projects, you are able to connect to ideas that are relevant to students, communities, and cultures. Collaborative projects, expansive framing, which means connecting to the real world. Randy Engel's work, I'd urge you all to read that, making socially consequential connections, talks with women in tech. The project itself has partnered with the Amazon Future Engineer Program. We haven't been able to run this in a classroom yet because of all the constraints we're under right now, but those are the plans, field trips, etc. And these are the various topics. I've already sort of touched on a lot of these already. But another thing I want to point out that they do get to work with data and lists in a very authentic, organic way, but they're working with multidimensional data. And one of the things that I also really appreciate about this curriculum and tool is that, learners experience firsthand the power and use of abstractions that bring powerful functionality within their reach so that they can explore advanced concepts and ideas. And many people say that they find it difficult to teach abstraction, but learners here are actually seeing it firsthand and experiencing it. So we ran a pilot this past summer. I'll talk a little bit more about it when I talk about the teacher PD. It was week 1 of a 3-week summer camp. The sample was mostly students, mostly girls, sorry. About 30 students were planned, 27 students participated, 25 agreed to sort of fill out, participate in the surveys and such. 19 boys, 6 girls, all except for 2 were students of color. And we had a wonderful project showcase where we actually invited creators of Snap from Berkeley, other friends of the project, Yasmin Kafai and others, Dan Garcia, Brian Harvey, and folks that created the BJC curriculum at EDC. The students actually found this very interesting. They commented on it in their post surveys, and they had an interesting mix of projects that they created. Many were related to COVID-19, just showing how it is so on top of mind for everybody, but also climate change, movies, all the things that we sort of had conjectured would be of interest to students. And so it was an overwhelmingly positive experience for students. And in the post survey, we did a pre-post survey, but in the post, we added a few additional questions. We asked students to rank projects in order of what they found most fun or interesting, and rank the ones they found to be most useful. We wanted to see how those two responses would vary. And we also asked them an open-ended response of how, if they had more time to work on the project, what would they do with RPCs and message passing skills, etc. And this was a very interesting data in that they were sensitive to the distinction between something being useful and even if it's not exciting. The data science tools were like that. They fit that bucket. Basically, the charting skill was found to be very useful, but not so much fun. And animations were the opposite. They found them to be interesting, but not necessarily useful. And some projects did great on both counts. They found maps and COVID-19 to be, projects that they were both useful and fun. And these are, we have, comments for that third question from all of them. But just want to point out that they themselves talk about how to make COVID data more relevant to local communities and neighborhoods. Both these responses are from girls. And one talked about we only basically are using maybe a couple of databases, but I want to combine many databases and make things really useful for a wide variety of information and such. And they all created these, a slide deck at the end of their 3-week project, but they all still talked about week 1, where they talked about, distributed computing, real-time COVID data. Many talked about, understanding SNAP better, which was very interesting. And maybe it's something to probe deeper. Even this student said that they'd help me understand SNAP, and they talked about problem solving and getting feedback from the showcase, etc. And so though we designed an experience with project-based learning and data science and collaboration and transdisciplinary learning in mind, what students felt they were getting was good problem solving, working with powerful ideas, computational thinking. They actually mentioned these in their various responses. And so that was great. Now, another deep breath for a moment. So this, I'm going to switch gears a little bit to talk about the teacher PD that we also conducted this past summer. But this was the Koli paper that was accepted, a short paper on this experience report, which is basically first principles to design for online, synchronous high school CS teacher training and curriculum co-design. We would have added in the time of COVID-19, but I guess there was limits to the title. And so it's this piece of research is basically about teacher PD with a set of teachers who also help co-design the lesson plans that they will be using in their classrooms. But it really is also about teaching and research in the time of COVID-19. So before I proceed, I want to discuss briefly why it is a great idea to co-design with teachers. And there has been research done on this. And it's basically that it's a mutually supportive exercise between researchers and teachers. The curriculum design benefits from teachers' classroom experience and a better understanding of students and their students. It's increasingly seen as an excellent form of teacher PD. So I really would urge everybody to consider co-design as part of teacher professional development. It involves collaborative activities with other teachers, which teachers always appreciate. And it brings a diversity of perspectives. So, it's great, even if the teachers they're sort of new to the topic that they're designing with you, but especially when it's them that you are going to probably rely on to actually do their first iterations of that curriculum in their classrooms. So it sort of becomes a very, rewarding experience for the researchers as well and the designers. So our teacher cohort comprised 7 high school CS teachers who the team knew through prior CS teacher PD and such. There were 7 high school teachers from North Carolina, Tennessee, and Massachusetts, 5 female, 2 male. Among the 5 female, 2 were African-American, 2 white, 1 Asian-American. All teach APCS principles or APC and or APCSA, and some of them also teach elective courses that they have created for their own schools like cybersecurity and such. So the pre-COVID plan, when this project first started, was for all of us to meet for 2 weeks in person in Nashville, Tennessee. And then based on past research on teacher PD on how collaboration works well at a distance, once teachers have sort of developed a relationship through in-person PD, we thought the co-design can happen remotely. And there was a possibility of a summer camp with high school students in Nashville. And we were still all deliberating all of this when our worlds came crashing down with COVID-19. And so, like the rest of the world, we decided that we would jump onto the Zoom bandwagon and make a go of it. But then what should a 3-week PD look like, especially one that has to replace a face-to-face PD? And I guess we grappled with a lot of the same questions that many of you and everyone all around the world wrestled with. And so we took inspiration from design-based research. And for those who are not aware with DBR, it's essentially a methodology for conducting research when design is involved, design of curriculum, PD, whatever. And some of the key attributes are that it's contextual, you do it in real settings, it's pragmatic, you usually use iterations to guide refinements. Often stakeholders engage as design partners, that's an important one. And your initial design basically embodies conjectures from research and your own past experience. And so the conjectures that we sort of started with were people are generally overwhelmed. Everyone has Zoom fatigue. There's uncertainty from day to day. Sorry for the typo there. Teachers would help guide the PT design maybe, and we would need lots of online supports for the teachers. And one of the things we decided on was this short cycle based feedback. Usually DBR interventions, you run a curriculum, then you sort of revisit the data, and sometimes you may do course correction in the midst of an intervention, but often it's at the end. But here we sort of decided to do it on a short cycle basis. And there's a paper that sort of describes this short cycle feedback really well. And so our initial design conjectures were that we would limit pre-PD work to a few key tasks. PD would largely be online and synchronous, so that it would replicate in person, but again, we wouldn't expect teachers to do much in their off Zoom time, because people's lives are too full with, we were talking about June. So, people were just sort of coming out of that first wave and lockdowns and whatnot. We would have short real-time sessions to prevent Zoom fatigue. There would be a mix of, even though it was supposed to replace 8-hour day-to-day, 8-hour sessions if we were to meet in person, we acknowledged that teachers had just too much going on, too much to contend with. And the coding pedagogy that we, decided on would include, live coding to explain distributed computing concepts while creating the projects, and the use, modify, create kind of pedagogy to help teachers develop fluency, etc. And then, we decided that there would be flexibility, because we didn't know how in the absence of in-person interactions, we weren't sure how teacher collaboration would work. We decided we would use teacher inputs on how to structure the off-Zoom work, because there was so much uncertainty on how much, we just couldn't plan ahead for a lot of the things, is what I'm trying to say. And that there would be a need for online asynchronous supports for interactions. And this was the rough 3-week schedule, which I think worked out really well, in that they were learning, then they were teaching, doing the summer camp, with a remote summer camp with students that were in North Carolina in our North Carolina site, university site, for a summer internship, and then co-design the curriculum. And the teacher training would include nets blocks, distributed computing, RPCs, message passing, and pedagogy, etc. And so what we ended up planning was a very light-hearted, welcoming pre-PD exercise of creating the NetBlocks account, playing with a distributed computing game. We framed the PD from the very beginning as being supportive and flexible. And I think that was important. We had fluidity in decisions of teacher group work. We involved teachers in decisions. We had about 3.5 hours of Zoom post-lunch for most folks, because they were all on the East Coast for the most part, East or Central. And they would use the morning time for preparation and other things. At the beginning of each day, we started with office hours for additional help, especially with the coding exercises. Zoom sessions were recorded, recordings were made available to teachers. We had a shared Google folder for sharing materials. We had a class group for on Piazza for asynchronous interactions, discussions, sharing ideas, and also pinning something that was important for teachers, time sensitive, and continuing conversations because our Zoom sessions were short. When we think about all that we had to cover, and there was daily feedback for short cycle DBR, and the research team met at the end of each day to review the feedback and plan ahead. And so this is roughly what the timetable looked like. I'm not going to go into it. Suffice to say that most of the time was in the coding, spent in coding with breaks and reflections, and there was pedagogy. These were the pedagogy topics that we covered. Things that I've already mentioned, but we used NCBIT resource. All right. So back to where we were. Is everybody can see my screen? I guess this is where I was. So we were talking about the pedagogy, and I should say that a lot of the structure of the PD was also driven by, inspired by a previous teacher PD that Tiffany and Veronica and others at NCSU had done with their Beauty and Joy of Computing teacher curriculum, teacher professional development work. This was the key part of our the daily activities. We got daily formative feedback. The last half an hour, we spent our time by ourselves, reflecting, debriefing, and responding to questions. And the questions that were asked were: what went well today? What can be improved as we move forward? What was one success you had today? Is there anything else you'd like to share? And at the beginning of the next day, we would share the broad feedback and the plan and how we had tweaked things. And that image you see in the back is sort of the spreadsheet of the responses for each day. What was cool was that we did a lot of iterations on this work, basically on our design of the PD. I'm not going to read all the responses. Suffice to say that we strictly adhered to time. We did not run over even by 10 minutes or 15 minutes, because even that was too much for teachers sometimes. We started creating live coding style videos. Brian and Akush would often create these videos for teachers to work with before live sessions on their own time in the evenings or the mornings. And sometimes they involved, adding a bug which teachers would need to fix or something. And there was optional but recommended homework sometimes. To think of other projects and applications that students could sort of engage with based on the ideas they had just learned. We did all these tweaks over the course of that week, and they were concerned about what the camp was going to be like, what the the collaboration, the co-design was going to be. So we made time for all of those. And by the end of the week, it really felt like the teachers were sort of getting comfortable and enjoyed a lot of it. And in the second week, they divided, the 7 teachers into 3 groups. They all worked with a group of 8 to 9 students through breakout Zoom rooms. They met on their own for planning sessions. They created slides and materials based on what they had just learned. And there was a daily pre-camp check-in with the researchers. And we even facilitated that final showcase that I talked about. In the third week, they were divided into 2 groups. This was all based on their own inputs of how they wanted to work. They collaboratively designed a template for the lesson plans. Each teacher created one lesson plan, but with help from team partners. And they basically also contributed to our broader thinking about the spiral buildup of projects, what prerequisites students would have to bring in, additional non-programming activities and connections that could be made, and such. And this was an interesting way in the way they divvied up in the weeks 2 and week 3. The week 3 was divided in a way that each group basically had the brains of every other group that had worked in week 2, because they all had created ideas for teaching those topics and projects. And so they wanted to sort of pool their collective resources in this way. And you'll have already seen this slide. This was the showcase that was done on the final day of the summer camp with the students. And as for teachers, we got their daily feedback. We had Zoom sessions and reflection sessions that we recorded. We had a post survey where we had Likert scale like items and open response items, where we asked these questions, how they might be able to incorporate these, what were the best parts, what can be done to improve, what follow-up assistance they would need if they wanted to teach this, anything else they'd like us to know. And of course, on the Likert scale, overwhelmingly great responses, very happy with almost every aspect. Since we're running short of time, I'm not going to spend too much time on the slide. Suffice to say that the lowest score was, the content was relevant to my professional responsibilities. Now, this is an elective course, and currently they're not expected to teach this course. And so that was the only one. But in everything else, they were really, really happy and positive, and that really made us feel great. And we coded the responses from the open-ended Zoom session, especially the final reflective session, as well as the responses on the survey. And on the curriculum itself, they were very excited about how this could be an option, an alternative to APCSA, how students can work with, pulling in data from resources, from web resources, and, passing information, how they can, incorporate it into particular units of APCS principles. Someone said they could incorporate it into their cybersecurity class and such. And collaboration was something that came out organically. We never asked in the post survey about how they liked collaboration in particular, in the open-ended response, but often in the what I liked best, they talked about collaboration with their peers, and as being one of the great points of this PD. And what else? They really just enjoyed working with each other throughout, even though it was all via Zoom, all, not co-located. The overall experience was overwhelmingly positive, and and it left us feeling really, happy with something that we had never done before, something like this during the time of COVID. And when we reflected on and coded the responses, we felt like the things that made a difference were flexibility, our flexibility in timing, pacing, teacher availability, decisions to shape the agenda, and the collaboration. The innovativeness, including, the summer camp where they would teach what they had just learned and then use both those experiences to bring to the co-design process, innovative ways of collaborating. Responsiveness and respect, giving teachers a voice in the design of the PD, seeking and responding to feedback throughout, the supports that we created, online spaces for interactions, office hours, asynchronous supports, recordings of sessions, and of course, collaboration and teamwork. And not just the teamwork that teachers enjoyed, it became the linchpin of their PD, it looked like, but also it was delightful for us as a fairly large distributed team sort of working together. And so these are our first principles, FIRST, for successful CS online CS teacher PD for COVID and post-COVID times, I guess. And with that, I will end. If you'll want to get in touch with the project, that's the Gmail account. And if you want to get in touch with me, those are the details.